The Greenland ice sheet, in contrast, is not grounded below sea level, but it is extra vulnerable because it's warmer at the surface. In Antarctica, the surface of the ice is always pretty much below freezing. And so the only way to melt the Antarctic ice sheet is to flow it off into the water and melt it in the water, maybe let it drift away up into warmer climates. But Greenland, it gets warm enough to melt at the surface, especially around the edges. And what seems to be happening is that meltwater from the surface is able to penetrate through the ice sheet and run down and lubricate the bed. And so there are fluctuations in the flow velocity of the ice according to the seasonal cycle. The way that, so they flow faster in the summer when there's more of this meltwater than there is in the winter. So without this mechanism, if the only way to get heat from the surface to the bed is by diffusion, by conduction of heat, it would take a very long time for a warming signal at the top to translate into faster flow of the ice. But with this meltwater mechanism, the ice is able to respond and flow much more quickly than it would otherwise. It's still sort of a mystery how this meltwater is able to get through all of this ice. This is supposed to be sub-freezing through here. So it's observed happening. Here you can see a photograph of what's called a moulin, where the water is running and just going down the drain into the ice sheet. But they can trace the water as it goes in here and comes out there. But mechanistically, it's difficult to understand how this works. So ice sheets are very complicated. The Greenland ice sheet in particular is very complicated. You have these regions of very fast flow called ice streams. So there seems to be some sort of a positive feedback mechanism that if the ice starts to flow quickly enough, the deformation crumbles the ice or melts it to lubricate the bed or something like that and allows it to keep going quickly. So there are places where ice streams are going very quickly and then suddenly stop and then start again. It's very sort of unpredictable and quirky. The ice sheet can be pinned by local islands and rocks and things like that, and then lateral stress can sort of hold the ice from moving. It'd be much easier if we could just model it in a one-dimensional sense, so the models that you'll be playing with in the lab are just one-dimensional models, but those aren't really good enough to capture everything that's going on. And then you have this ice shelf here, which can also act to sort of buttress the ice, for, sort of slowing down its rate of flow into the ocean. So after the ice shelf on the Jakobshavn glacier in Greenland collapsed, it was observed that the flow coming down the mountain into the sea about doubled. So there are all these different pieces that have to be put together to predict how an ice sheet will respond to changes in climate. There are some lessons from the past that make this particularly worrisome. One is a trace of sea level through time through the last deglaciation. So sea level was 120 meters lower during the last ice age. And when it rose to form the interglacial world that we live in today, it didn't just rise in a smooth way, but it seemed to go in pulses. And in particular, there was this one interval called meltwater pulse 1A, which was a huge amount of water, a very large change in sea level in a very short time, and glaciologists aren't even sure where this water came from. Another class of events from the paleo record is called Heinrich events. So these are, what's left behind today are layers of pebbles in the sediments of the Atlantic Ocean. And they're much too big to have been blown there by wind or something like that. They are they must have been carried in ice. They are called ice-rafted debris. So at various specific times in during the glacial time, the Laurentide ice sheet, which was the ice sheet in North America, seemed to just collapse and dump vast armadas of these icebergs carrying these little pebbles into the Atlantic Ocean, and they made these layers of ice-rafted debris that we can find and see today. Trouble is that models of ice sheets can't generate this much ice-rafted debris. So it's clear that ice sheets know a trick or two about melting that we are only now figuring out. And if anything, the models that we have for the ice sheets and their response to climate are probably too sluggish. Storms are expected to intensify in a warmer world. And this is because water vapor is kind of like the nitroglycerin of the atmosphere. Have you ever seen those cowboy movies where they've got, the stagecoach full of nitro that they're going to use to do some mining or something like that, and they got to carry it around without shaking it too much because it could just blow up? Well, water vapor is kind of the same way. Water vapor, when it condenses, releases latent heat, which then drives motion that drives more water vapor to condense. And so all of the explosive weather that we have is due to water vapor. And as I said before, in a warmer world, there will be more water vapor in the atmosphere. So that tends to make the weather sort of stormier. Hurricanes are kind of one of the things that people think about the most. Hurricanes are complicated. They form from sort of very specific kind of seed weather events, particular kinds of winds sort of blowing off of Africa. And then whether they sort of grow into formation hurricane or not depends on real subtleties of the atmospheric circulation, like the presence of wind blowing in different directions at different altitudes, which is called wind shear, tends to break it apart before it grows into a bigger sort of an event. So there's not a real strong theory for why we tend to have a certain number of hurricanes every year. And it's not at all clear that climate change is going to alter that. It could, apparently, but it's sort of, some aspects of the climate change forecast are very easy, like a global average temperature is sort of constrained by large-scale energy considerations. Regional climate changes are not so easy to get, and then things like hurricanes are, really the devil's down in the details, and so it's hard to predict. But making the sea surface temperature warmer is thought to provide more power for the hurricane. The hurricane derives its energy from the water vapor that it gets from the water surface. When a hurricane starts going over land, it starts to decrease its intensity and die. That's because it doesn't have access to the water vapor. So making the sea surface temperature warmer is thought to make hurricanes stronger. On the other hand, making the upper atmosphere warmer would tend to negate some of the impact of making the surface warmer. And what is actually observed is that the hurricanes in the last few years seem to be getting stronger even than simple theory would predict based on thermodynamics of the temperatures and the heat engine that is a hurricane. So it's kind of a loose cannon in the forecast what will happen in the future, and there are reasonable and concerned people on both sides of this question. It's not really well answered, but the way that models respond to a change in temperature is to shift the frequency distribution of the hurricanes a little bit toward the stronger. And if we have these categories, category 3, 4, and 5 hurricanes, where the category 5 was just a little tail of the distribution in the natural world. If we shift this distribution this way, suddenly the proportion of them that are these category 5s could go way up. So in general, there are expected to be, and are already observed to be, more intense rainfall events, more heat wave events. In general, a heat wave driven by greenhouse gases tends to not relent at night as much as a natural heat wave would have. By putting more CO2 in the atmosphere, you're making it hard for energy to leave the planet. And so the real killer is that at nighttime it doesn't cool down and sort of give everybody and everything a chance to kind of recover in the same way. And heat waves are potentially problematic for agriculture because there are sort of thresholds. About 90 degrees Fahrenheit, or around there, 95 is a threshold for corn, for example. If you have too many days above that, suddenly the crop can kind of fail. There are different aspects of storminess. There's hurricanes, there's thunderstorms, there's floods, and they're all sort of affected by climate change differently. But in general, we can sort of summarize by saying that the severity of extreme events is expected to increase in a warmer world. There are impacts to the natural world of climate change. Basically, warming the planet up means shifting the climate zones of the planet. And this is already observed to have happened. In this animation from the Arbor Day Foundation, you can see the hardiness zones have migrated northward just in the last few decades. So if you're going to move these climate zones, it's not so easy to move a forest. So this forest may suddenly find itself in unfamiliar climate territory to which it's not suited, and that could leave it vulnerable to sort of collapse or encroachment or fire or something like that. Other aspects of the biota can move more quickly, like insects can move basically instantaneously. So one thing that has been happening in the US is a particular kind of insect called the pine bark beetle, which is encroaching into the Rocky Mountain states. And it used to be kept in check by cold enough temperatures in the winter to keep its population down, but things have been so warm that they are killing vast stretches of forest in the Rockies. Climate zones move on mountains, move to higher elevations. And so the rainforest in Australia, in Queensland, is sort of located in the mountaintop sort of areas, climate zones which will disappear as climate changes. And so these are the species and ecosystems that get hurt the most, the ones that are basically chased off the map by the changing climate zones. Another example of that is in the high latitudes, where we're losing climate zones that used to sort of tundra and sea ice that supported, for example, the polar bears. So polar bears require sea ice as part of their life cycle. And when the ice is gone, there's no place for them to go. There are also possibilities of sort of add-on impacts to the human infrastructure. We think of our society as very robust because we're very powerful. We have all this industry and the agricultural revolution. There are more people on the earth than ever before, and our might seems infinite. But if some huge event triggers mass migration of people, say if Bangladesh floods or the river valleys in China, which are very low level, become uninhabitable or something like that, if you have mass numbers of people in distress who are moving, this could put a challenge to civil governance. You could have failed states and collapse of this infrastructure on which we all depend. I don't know if you've ever tried to grow tomatoes in a garden, but if you imagine trying to live off of your garden, you'll realize that if they didn't put food in the grocery stores for us, none of us would probably survive. So, and it's known from history that societies do just suddenly collapse. So this is also something to worry about.